So today we are going, good morning everyone. Today we are going to discuss everything with respect to cycloalkanes. So the name of the topic is cycloalkanes. And so what are these basically? So what is the definition of cycloalkanes? These are the alkanes which have some of their carbon atoms arranged in a ring. That means when alkane molecule will be joined or arranged itself in a ring format, those type of compounds are known as cycloalkanes. But those rings are of different sizes, beginning with the 3 carbon atoms are possible. So when alkane molecules are joined with each other in a ring format, so those type of alkanes are known as cycloalkanes. And in order to achieve this arrangement, that is ring arrangement, a alkane molecule must contain at least 3 carbon atoms. म्हणजे minimum 3 carbon atoms present asnara's molecule will go further for the formation of cyclic ring. So our first cycloalkane is cyclopropane, as it is going to possess 3 carbon atoms in its structure. So cyclopropane followed by 4 carbon atom containing cycloalkane molecule, cyclobutane, 5 carbon atom containing alkane molecule, which is arranged in cyclic format, is known as cyclopentane, and the last, which will possess a 6 carbon atom in a ring, is known as cyclohexane. So those are all the examples of cycloalkanes. As alkane molecules arranged in cyclic manner, so those are known as cycloalkanes. So these are, what are those? These are basically saturated. See, the carbon-carbon atoms join with each other with the help of saturated bonds, single bonds. All the carbon atoms that make up the ring are single bonded to other atoms. In case of cycloalkanes, individual carbon atoms join with each other with the help of carbon-carbon single bonds. Because of the ring, a cycloalkane has 2 fewer hydrogens than an acyclic alkanes. Due to this cyclic arrangement, they are going to have 2 more hydrogens than the non-cyclic carbon atom, non-cyclic alkanes, with the same number of carbon atoms. So there is addition of hydrogen atoms. The general molecular formula for the cycloalkane is, what will be the molecular formula for the cycloalkane is CnH2n. So whenever we are going to derive any molecular formula with respect to cycloalkane, so this is a general formula. What is that? CnH2n. So this is a definition of cycloalkane molecule. Now, how we are going to nominate or nomenclature of cycloalkanes? If we are going to give the name to the cycloalkanes, so in which manner, in what manner we are going to give the names to those cycloalkane molecules? So cycloalkanes are commonly drawn as line structure. So in this manner, we will going to draw the structures of those cycloalkanes. See, in last slide we have seen the hydrogen carbon structure of cycloalkanes. So those structures we can draw in this manner also in the form of line. This is cyclopropane, cyclobutane, cyclopentane, and cyclohexane respectively. So we can draw these structure in the line format. So cycloalkanes are commonly drawn as a line structures, whereby each vertex represents a carbon understood to be connected to an appropriate number of hydrogens to give the carbon 4 bonds. Whenever they are going to form a vertex or an angle, while joining the carbon-carbon with each other, So there is addition of two more hydrogens so that this carbon atom or individual carbon atom in the cyclohexane molecule will satisfy the valency of carbon atom, that is 4. Cycloalkanes are named by adding the prefix. How we are going to give the name to the cycloalkanes? By adding the name prefix cyclo to the name of alkane. See, the cyclo prefix we have given to the name of first alkane, which is arranged in cyclic manner, that is propane. So the name of this particular compound we can nominate as a cyclopropane. Name of this particular alkane, as it is going to have 4 carbon atoms, the name of this particular alkane is cyclobutane, followed by pentane, that is cyclopentane, followed by hexane, the name is cyclohexane. These most common cycloalkanes are represented as below. So in this manner, we are going to represent the cycloalkane molecules. Now, this is unsubstituted cycloalkanes. So the nomenclature of unsubstituted cycloalkanes. So we can nominate in this manner: cyclopropane, cyclobutane, cyclopentane, and cyclohexane. But if cycloalkanes are substituted. So what are the nomenclature rules for nominating substituted cycloalkanes? So the nomenclature rules for substituted cycloalkanes are same as like that of substituted alkanes. सबस्टिट्यूटेड अल्केनचं नॉमेनक्लेट करण्यासाठी जे काही रूल आहेत ते सेम रूल्स आर ऍप्लिकेबल टू द सबस्टिट्यूटेड cycloalkanes. So what are those rules? The rule for naming cycloalkanes are similar to those used for straight chain alkanes. So those rules are same. What is first rule? The parent ring is largest ring in the molecule. So in the case of unsubstituted alkanes, that is alkanes, we are going to select a parent chain. So here we are going to select a parent largest ring. Instead of chain, only the ring is there. The parent name is generated by adding prefix cyclo to the name of the alkane. Then identify the substituent. So in case of alkane, we are going to identify the substituent. Same here, identify the substituent and their location, at what position it is located, by numbering a ring from the carbon containing substituent so as to give the substituent the lowest possible location number. Then according to alphabetical order, the substituent in the full name of the cycloalkane. So we are going according to alphabetical order, chronological order. We are going to arrange those substituents, their names, and we are going to complete the name of that alkane molecule. So this is with respect to cycloalkane. What is cycloalkanes? What are the examples of cycloalkanes? What will be the rules for nomenclature of cycloalkane? This is an introductory part, what we have discussed up till now. But your syllabus contains these many points. So what is there in your syllabus? So from syllabus point of view, respect to cycloalkane, we are going to study the stabilities of cycloalkanes, whether they are stable, whether they are unstable, and for those stabilities, to study the stabilities, we are going to discuss some of the theories which is put forth in front of us by different scientists, different group of scientists. So what are those theories? So for that, to study the stability of cycloalkane, we are going to study different theories. Theory number 1, Bayer's strain theory. This theory has its own limitations. We are going to discuss the limitations of those theory, that is Bayes' strain theory. Second theory we are going to discuss is Colson and Moffat's theory. And third and last theory we are going to discuss is Sachet-Morse theory. It is also known as theory of stainless rings. This is part number 1 we are going to discuss with respect to cycloalkanes. Followed by in part number 2 we are going to discuss methods and preparations, reactions of only two cycloalkanes, that is cyclopropane and cyclobutane. So our first theory of cycloalkanes is Bayes' strain theory. Now, what is the criteria or features of this Bayes' strain theory that we are going to discuss in detail? This theory, introductory part with respect to this theory will discuss the stability order of cycloalkane. Now, what is this theory actually? Bayes' theory is based upon some assumptions, some postulates, some tattva. So it is depending upon some of the postulates that are helpful to understand instability of the cycloalkane ring system. When we are going to compare a ring, that is cycloalkane with alkane, cycloalkanes are unstable or unstable when we are comparing with the alkanes. So what is the reason? काय कारण असेल की cycloalkanes हे stable नाही आहेत कुणापेक्षा अल्केन पेक्षा, आणि तेच कारण आपण इथे आज डिस्कस करणार आहोत. So these are the assumptions of Bayes' strain theory. Why they are unstable than the alkane molecules? So what are their assumptions? All the ring systems are planar. So we have seen the structures. So these are in one plane only. So all the ring structures are planar. Deviation from normal tetrahedral angle results into its unstable cycloalkane. The larger ring system involve negative strain, hence do not exist. So these are the features. We'll discuss individual features in detail in coming slides. So our first feature of Bayes' strain theory is all the rings are planar, but there is deviation from normal tetrahedral angle. This is first postulate. Second postulate is larger ring systems involve negative strain, so do not exist. Third postulate, the bond angle in the cyclohexane and higher cycloalkanes, that is cycloheptane, 7 carbon containing cycloalkane, octane, 8 carbon containing cycloalkane, 9 carbon containing cycloalkane, that is cyclonone, etc. These are not larger than 109.5 because the carbon rings of those compounds are not planar in nature. Now, these are the assumptions of or postulates of which theory? Bayes' strain theory. How many postulates are there? 3 are there. Now, we'll discuss individual postulates in detail. Adolf Bayes in 1885 proposed this theory, which is named as Bayes' strain theory. Proposed a theory to explain the relative stability of the first few cycloalkanes on the fact that normal angle between any pair of bonds of carbon atom is 109.28 degree in the tetrahedral geometry. Well, so we will discuss the first postulate, that is deviation from normal bond angle. Now, when any carbon atom having its own valency 4 When it is joined with 4 carbon atoms, that is in sp3 hybridized state, the bond angle, we know the sp3 bond angle tetrahedral geometry, the bond angle between these two hydrogen atoms which is joined with the carbon atom is a normal bond angle, that is 109.5 degree centigrade. We know this bond angle when the carbon atom is joined with another atoms in a tetrahedral geometry. So the tetrahedral geometry bond angle is 109.5 degree centigrade. Bayer postulates that any deviation from this bond angle, which bond angle? Tetrahedral bond angle from the normal tetrahedral value would impose a condition of internal strain on the ring, and this strain is known as angle strain. See, when carbon is joined with sp3 hybridized tetrahedral geometry, the bond angle is 109.5 degree centigrade. But when in the case of cyclopropane or cycloalkanes, the carbon atom in sp3 hybridized state, the bond angle is 60 degree centigrade, but it is not at 109.5 degree centigrade. See, in the case of only propane, the bond angle is 109.5 degree centigrade. But when this propane will join in a cyclic manner, the bond angle is changed. This changed bond angle will impose a strain on that carbon atom, and that strain is known as angle strain. And this information and this postulate is given by the Bayer. That's why it is an first postulate. Basically, the carbon has to achieve this bond angle in the tetrahedral geometry. In the cyclopropane also, all the carbon atoms are sp3 hybridized. Then also they are going to deviate the bond angle. Basically, त्यांनी कुठला bond angle achieve केला पाहिजे? 109.5. But they are not achieving this. They are attaining the bond angle of 60 degree centigrade. So this will be the deviation of bond angle from tetrahedral geometry to the 60 degree centigrade. This deviation is known as angle strain, as they are joined with each other in a 60 degree angle. Understood? Now, Bayer proposed that the optimum overlap of atomic orbital is achieved for bond angle of 109.5 degree centigrade in a molecule if it is sp3 hybridized. In short, it is an ideal bond angle for the alkane compound, which produces maximum bond strength and stable molecule. When carbon atom is sp3 hybridized, it should त्याने हाच बॉन्ड अँगल अचीव केला पाहिजे. विच बॉन्ड अँगल? 109.5 bond angle. But it is not with respect to the cycloalkane. When carbon atoms are joined in cyclic manner, they are deviating. ते त्यांचा बॉन्ड अँगल चेंज करतात. 109.5 पासून ते कुठे डेव्हिएट होत आहेत? 60 डिग्री सेंटीग्रेडला डेव्हिएट होत आहे. म्हणूनच that's why as they are deviated from this bond angle, that's why they are going to change their stability. They are unstable because of their deviation from the tetrahedral geometry bond angle. So that's why cyclopropane is less stable than the propane molecule because of the deviation from the normal bond angle of tetrahedral geometry. For an open chain compound, that is propane, when carbon is connected to two other, that is carbon atoms, as it is sp3 hybridized, they are going to give the bond angle 109.5 degree centigrade. But in the case of cyclopropane molecule, the bond angle is changed. There is deviation from the normal tetrahedral bond angle. This deviation will give the strain in this ring, and that strain is known as angle strain. If bond angle deviates from the ideal, then the ring produces strain. Pressure येतं त्या carbon atom वरती. स्ट्रेन येतो, ताण येतो त्या कार्बन ॲटम वरती, इट इज नोन ॲज रिंग स्ट्रेन or it is also known as angle strain. Higher strain produces higher instability. Higher will be the strain, higher will be the instability. Increased reactivity. See the relation between these terminologies. Higher strain, higher instability. Higher strain increases reactivity, increases heat of combustion. We have to give the more heat to break these bonds. In simple, higher the deviation, lesser the instability. So this is with respect to the angle strain and ring strain. Now, how much deviations are there with respect to individual cycloalkanes? So we are observed that different bond angles for different cycloalkanes. Now we have seen one deviation as it is deviated from normal tetrahedral bond angle, that is 109.5 degree centigrade, and the bond angle in case of cyclopropane is 60 degree centigrade. So how much deviation is there? So we are going to minus it the value of deviation. 109.5 minus 60 will give the 49.5 degree centigrade deviation. Then, so we are observed that different bond angles for different cycloalkane and observe some different properties and stability. So on this basis, he has proposed the angle strain theory, which will explain the reactivity and stability of cycloalkanes. So these are the bond angles of all those cycloalkanes. The bond angle for cyclopropane is 60 degree centigrade. The bond angle for cyclobutane is 90 degree centigrade. The bond angle for cyclopentane is 108 degree centigrade. Now, how much deviation is there? So we are going to just minus it the value of bond angle from the tetrahedral bond angle. So what will be the result? 109.5 minus 60 will give the deviation of 49.5. 109.5 minus 90 will give the deviation of 19.5. 108 minus, okay, 109.5 minus 108 will give the deviation of a negligible deviation, that is 1.5. In case of cyclohexane, the bond angle is 120 degree centigrade and the deviation is minus 10.5 because we are subtracting the higher value than the lower value. So the angle strain, it is in minus. Now, how we are going to calculate the angle strain? Angle strain is nothing but the deviation divided by 2. Deviation divided by 2 is nothing but the angle strain. So the different cycloalkanes will give different angle strains depending upon their bond angles. More will be the angle strain, more will be the reactivity, lesser will be the instability or instability. Karan, that means cyclohexane is more reactive. Now, in this manner, we are going to calculate the deviation. This carbon atom, when it is in tetrahedral geometry, it should achieve the bond angle of 109.5. But this is not the case with the cyclopropane. They are going to strain their chain. They are going to make the pressure on the bond angles of the carbon atom to achieve the bond angle of to achieve the bond angle of 60 degrees centigrade. So this much of strain attained by these two carbon-carbon bonds, This strain is known as angle strain. I hope you have understood, everybody, what is the meaning of the word angle strain. And these are all postulates given by the Bayer. So this theory is known as Bayer strain theory. The ring of the cyclopropane is in triangle shape. All the three angles are going to have the bond angle 60 degrees centigrade in spite of tetrahedral bond angle 109.5 degrees centigrade. The normal bond angle for carbon atom. This implies that normal tetrahedral between the two bonds is compressed by 60 degrees centigrade, which will give the angle strain of 24.75, which will represent the angle strain or the deviation through which each bond angle obtained from the normal tetrahedral bond angle. So in the same manner, there is deviation from the normal bond angle with respect to the cyclobutane. It is 90 degrees centigrade. With respect to the cyclopentane, it is 108 degree, and with respect to the cyclohexane, it is 120 degrees centigrade. Now, the deviation for the cyclopropane and cyclobutane ring systems, the normal tetrahedral angle will produce a strain in the ring. This will produce a strain in the ring. The ring strain will make them unstable. That strain which will be making the pressure on that carbon-carbon bond angles will make the compound unstable as compared to the molecules having tetrahedral geometry. So according to Bayer, cyclopropane should be highly strained molecule and most unstable compared to the cyclobutane. The triangle ring therefore be expected to open up slight provocation, slightly more, by a normal reagents, that is Br2, HBr and H2. Now the angle strain of cyclopentane is 0.75 degree, considered to be under least strain and should be most stable. Thus, it is not surprising that it does not undergo ring opening reaction. That's why cyclopentane is more reactive than cyclobutane than cyclopropane. So this is with respect to the angle strain theory, which is put forth in front of us by the Bayer. But there are some limitations. What are those limitations of Bayer's angle strain theory? Bayer was not able to explain the effect of angle strain in larger rings. He has explained with respect to the cyclopropane, cyclobutane, cyclopentane, and cyclohexane. Only this many molecules he has explained in detail. But he has not explained anything about cycloheptane, cyclooctane, cyclononane, cyclodecane. He has not explained about these molecules. This is a limitation of this theory. According to Bayer, cyclopentane should be much stable than the cyclohexane, but it is not practically possible. या theory अनुसार cyclopentane is stable than the cyclohexane, but this is not the case with the practical. But generally, it is not possible. So this is a limitation. Larger ring systems are not possible according to Bayer ring theory because there is negative strain exists. We have seen the example of cyclohexane. The angle strain is negative -5. The angle strain is -5 to the -5. So he also unable to explain these negative values with respect to the higher cycloalkanes. Larger ring systems are not planar but ring-curved to eliminate the angle strain. So he enables to explain the angle strain with respect to higher alkanes These are the limitations of Bayer's strength theory. So what we have discussed, the angular strength cyclohexane is higher than that in the case of cyclopentane. This theory increases continuously with increasing in the number of carbon atoms in the ring. According to this theory, cyclohexane and higher cycloalkanes should become increasingly unstable, and hence instability will result into more activity. Contrast to this prediction, cyclohexane and higher members are found to be stable. So this is a limitation. They do not undergo addition reaction. Instead, they react by substitution reaction. This is a limitation. Thus, the theory satisfactorily account for the first three cycloalkane. That means this theory is only applicable to only three first cycloalkanes, that is cyclopropane, cyclobutane, and cyclopentane. That means angular strength theory only applicable to the first three cycloalkanes, that is cyclopropane, cyclobutane, and cyclopropane. So this is with respect to the first theory which put forth in front of us, that is Bayer's strength theory. What we have discussed today,